And all right. Hi, everyone. Welcome to seminar on optimization, algebra, and geometry. Here, we are pleased to have Professor Serkan Hossein from San Francisco State University. Serkan is going to talk about Gram spectrohedra of symmetric binary forms. Thank you.
Thank you, Ali. Thanks for inviting me to give this talk. I appreciate you being here. So my name is Serkan Hossein from San Francisco here. I'll tell you. So this is work that I've done over a year or so, primarily with a master's student here at San Francisco State. And there's a lot more to be said about this topic, but I chose some parts of it, to tell you for 30 minutes. Yeah. So if you have any questions, there's not many people here. Just please stop me, and then we can talk. Yeah. So just a brief thing here. This is really based on two pieces of work. One of them is already published. I just put here the archive number, so in case you want to look at it. The archive paper is actually more stuff than the actual published paper. This is based on work with Alexander Heaton and Isabel Shankar. At the time, Alex was a postdoc and Isabel was a grad student, but both of them are tenure track faculty now. And Matthew Hyde was a master's student here. And this paper, what I'm primarily taking this out from, is going to be posted very soon, within the 2-3 weeks. We're almost there. So I don't think I need a lot of things about this one, this piece for this crowd. But my motivation comes to study this from polynomial optimization. We know if I have a polynomial, I'm trying to the minimum of this polynomial over real numbers. It's a very hard problem, but one can relax this problem and ask, and turn this into a feasibility question where we're looking for a sum of squares representation of a polynomial. Yeah. So given a polynomial, can we decide is it sum of squares or not? Yeah. That's one of the important questions we can ask. The answer is yes, right? And this turns out to be a feasibility question for a semi-definite program. If I have a polynomial in n variables, a real polynomial of n variables of even degree 2D, this polynomial is going to be sum of squares polynomial, if and only if it can be represented through a positive definite symmetric matrix. Yeah, I hope you're familiar with this. I write, so if the degree of my polynomial is 2D, I list all of the monomials in n variables up to degree d, okay, in a vector, and I put it, sort of transpose on one side, the vector on the other side, and I put in the middle a symmetric matrix so that I can express the coefficients through the entries of this matrix. And then for the polynomial to be sum of squares is equivalent to this matrix being positive definite. Okay. And again, so what I'm saying here is that so the coefficients of this polynomial can be represented as linear functions of the entries of the symmetric matrix. And I'm asking the question, I'm saying that, hey, can you find the matrix, given the polynomial, right? Can you find the symmetric positive definite matrix which satisfies some linear equations, i.e., the question is, given this polynomial, there is a certain spectrahedron, a positive definite cone intersected with an affine space. Is that spectrahedron empty or not? Yeah, that's the question. So this feasible region of this semi-definite program, which I'm going to denote by G plus P, I'm going to call the Gram spectrahedron of this polynomial. And every point, i.e. every matrix in this Gram spectrahedron parameterizes, right, all possible ways of writing this polynomial as a sum of square polynomial. Yeah. So my main objective study is this spectrahedron given a sum of square polynomial. Okay. Just a very, very basic quick example, right? Let's take a polynomial of degree 2 in one variable. I write this, it's 5x squared plus 2x plus 2. And I tried to find a sum of square representations of this guy. So indeed, there is a positive definite matrix in the middle you can put. You can factor it as, you know, AA transpose kind of factorization, and that immediately gives you the actual sum of square factorization, yeah, way of writing it. And now we can ask, given this polynomial, tell me all possible ways of writing it. Yeah, what are the symmetric positive definite matrices that I can use for it? Okay, so the overarching question here is that I'd like to study the gram spectrahedra of sum of square polynomials. Yeah, so these are very special kind of spectrahedra, and it would be great to understand them. Now, just a quick sort of remark here. My title is about gram spectrahedra of symmetric binary forms. It's a very specialized polynomials. The binary forms, of course, have been studied classically, yeah, from many different ways. And the gram spectrahedra, i.e. sum of squares versions of them, have also been studied classically. And I'm going to tell you a little bit about that. But we want to sort of look at this case where we look at symmetric binary forms. Yeah, it's very, very specialized case, and it fits sort of into a more general framework of study, you know, that I've done. Yeah. Okay. So here's an example. I'm going to use this example in the future too. So here is a general binary sextic. Okay, it's a polynomial in two variables, homogeneous, of degree 6. Yeah, such a polynomial can be parameterized by 6 real coefficients, a1 through a6. I'm assuming the first coefficient is equal to 1. Yeah, and for this polynomial to be sum of squares, I claim the 4x4 matrix you see here, okay, you see here, has to be positive definite. Yeah. So the coefficients a1 through a6 appears in this matrix, and then there are x1, x2, x3. Those are sort of the parameters, other parameters, meaning that there is the sum of squares. There is like a dimension, 3-dimensional worth of binary sextics that happen to be sum of squares. Yeah, I can put x1, x2, x3 there and make sure that this matrix is non-positive definite, and I will have a positive a sum of squares binary sextic. Okay, it's very easy to write this down, and just sort of you have a picture in mind. Here is that spectrahedron. Yeah, so I picked one binary sextic that happens to be sum of square. Okay, and I figured out, right, what are the x1 and x2 and x3, all possible x1, x3, x2. That's going to make, it's going to give that sum of square polynomial to be. Yeah, and it's this 3-dimensional spectrahedron. Yeah, just sort of you get a picture of that. Okay, so let me tell you something sort of recent, but in the same sense, sort of so classical too. And so here is a theorem by Klaus Scheidler, okay, from 2018, very recent. And it says in one of his papers, he proved the following thing. Suppose you have a strictly positive homogeneous binary sextic. Yeah, so one of the polynomials that I just mentioned. In this case, the gram spectrahedron is always 3-dimensional. Okay, and the interior of this spectrahedron consists of PSD matrices that happen to be rank 4. Yeah, these are 4x4 matrices, have to have full rank. Yeah, but moreover, we know some more. This gram spectrahedron, like the one you see here, yeah, does not have any faces of dimension 1 or 2. Yeah, it does have extreme points, okay, of very low rank. In particular, we can ask what are extreme points on the boundary of this spectrahedron, which have rank 2, let's say. Yeah, and it turns out there are at most 4 of them. Okay, there are 4 extreme points that corresponds to rank 2 matrices, and everything else on the boundary have rank 3. Yeah, so this spectrahedron can be sort of partitioned, you know, into, in general, 4 rank 2 matrices, a lot of rank 3 matrices on the boundary, and then rank 4 in the middle. Yeah. Moreover, and here is something that comes out of this result. It says that if you have such a binary sextic, yeah, and you take the line segment, okay, the line segment between any of these two rank 2 matrices on the boundary, yeah, there are 4 of them in general, okay, and if you draw the line segment, it's going to be in the interior of this spectrahedron. So of course you might say, yeah, I mean, why not, right? I mean, if you try to imagine this in this picture, you're going to have 4 rank 4 matrices, okay, and if you draw the line segment between them, it should be in the interior, but this actually changes once the degree increases, right? And here is the next degree case. I'll tell you again from Klaus Scheider's paper from 2018. This time I'm looking at a sum of square binary octet. Okay, so binary forms, in the case of binary forms, non-negative polynomial means the same thing as sum of square polynomial, right? By Hilbert's classification. So I'm looking at such a polynomial. In this case, there will be exactly 8 extreme points of rank 2. There will be exactly that many of them, and you can take any pair. You know, there are 28 pairs, and if you take the line segment between any pairs of these rank 2 matrices, the matrices, each line is going to lie on the boundary of the spectrahedron. Okay, it's going to be contained in the boundary. It's not an interior. So the binary sextic case is an exception. Yeah, so that it's going to be on the boundary. Moreover, out of these 28 line segments, 16 of them, okay, 16 of them happens to be a face of the spectrahedron. Okay, it's not only on the boundary, but it's actually a face. In fact, if you draw the graph, okay, of these edges of the spectrahedron, you get a graph isomorphic to K44. So it's like this. There are 8 extreme points of rank 2, yeah, and you can partition these 8 extreme points of rank 2 into 2 classes, and the edge between any of those guys between going from one class to the other one happens to be an edge, one-dimensional face of the spectrahedron, whereas the edges between the other guys among themselves are not. They're on the boundary, but they're not. Okay, so there's this interesting geometry going on there, and we wanted to explore these kind of things a little more. Yeah. In particular, let me just tell you a brief thing here. I'm not going to go into details about what we have done more, but so just on the side. So if you take one of these things, yeah, take a binary octet. Let's make it generic so that there are exactly 8 extreme points of rank 2. What we can do is we can take the convex hull of those 8 guys. Yeah. So you're going to get a polytope, yeah, with 8 vertices. It happens to be the case that this polytope, okay, is a simplicial polytope. It sits inside the Gram spectrahedron of the binary octet. It is one neighborly, okay, i.e., every vertex is connected to every other vertex by the edge segments that I already mentioned. Yeah, and there are exactly 2 combinatorial types of these polytopes. Yeah, since the sort of the codimension of this polytope is low, one can use techniques from Gale diagrams to classify these polytopes, and then we get that. So this polytope sits inside the Gram spectrahedron is possibly an approximation of the Gram spectrahedron, and then one can study actually the polytopes that are convex hulls of these extreme points of rank 2 for higher degree binary forms as well. And we've done that, but again, this is not something that I want to discuss much today. Yeah, but I want to mention this, that there is this interesting combinatorial geometry is also going on. Yeah.
Sorry, just a quick question. What
Yes.
is BP squared F?
BP squared F is the convex hull of the. So I have a binary octet, which happens to be sum of square. It's generic. I look at this Gram spectrahedron. It has 8 rank 2 extreme points. Yeah. always for a generic guy. And I'm taking now the convex hull of those eight extreme points. And I get a polytope. I'm going to call it P2F. Yeah. P2F. And I'm trying to, the sort of the long-term project here is that to compare this polytope, to the spectrahedron, how much they differ, what's the facial structure of the polytope versus the facial structure of the spectrahedron, etc. Yeah. And this can be done for higher degree binary forms as well. Yeah. But I'm going to just say the octet case.
Is it true that there are only 2 neighborly 4 polytopes and 8 vertices, so you get both combinatorial types?
Actually, no, there is more. So if you look at the Gale diagram, yeah, so you have 8 vertices, right? Its codimension is 1, so it happens to be on one line. The black and white points, if you know what I'm talking about, yeah. So there's actually some more kinds. I believe, and there's only 2 of them that's realized here. Yeah. If I'm saying something wrong, please forgive me. Okay, but I think there is more. Yeah. Okay. So anyway, so this was sort of the general case. So now I want to shift to the symmetric version. Yeah. Okay, I need to go fast. so now look at the following case. Suppose I have a group like Sn, okay, acting on my polynomial, yeah, on my polynomials, and this is of course going to give me a representation, okay, of polynomials of degree d. Yeah, this is a vector space, and then the symmetric group is going to act on that. That's going to give me a representation. Okay, so from here we can consider the following set, which is called the fixed point subspace. So the fixed point subspace is the set of symmetric matrices of the appropriate size, okay, such that the action, the orthogonal action of these representation matrices, okay, fix Q, okay, fix Q. So again, this is the way of saying that the induced action, okay, of the symmetric group, okay, fixes the set of symmetric matrices. Yeah. All right. So these matrices, okay, which are in the fixed point space of this action of the symmetric group, happens to be precisely those symmetric matrices which parameterize all symmetric polynomials. Okay. So I'm not looking at all polynomials anymore. I look at all symmetric polynomials. Yeah? So I have to look at this fixed point space. This kind of thing has been introduced actually in the polynomial, is sort of in the optimization literature by Karin Gatterman and in a paper by Karin Gatterman and Pablo Parillo. Okay, one can show that if a group is acting on your semi-definite program, yeah, then you can solve a smaller semi-definite program by using just this fixed point space. Yeah, so it's kind of a sort of a dimension reduction idea. Anyway, so the utility of this the action is that these matrices in the fixed point space, after a very clever change of basis, okay, can be written as block diagonal matrices. Yeah, where the diagonal matrices, the block matrices along the diagonal are forced to be positive definite if you want your original matrix to be positive definite as well. Yeah. So by this change of basis, you can simplify your matrix. Yeah. So again, I'm not going into a lot of details here. Okay. But this is sort of again, it's like a reduction in the complexity of your possibly your semi-definite program. Yeah. So let me skip this example. Yeah. Okay. So with this, I want to introduce the following concept. Yeah. So we have the PSD cone, of course, of whatever size matrices. But now we can look at all positive definite matrices which happen to lie in the fixed point space of the action of the symmetric group. Okay, so I'm going to call this the symmetry adapted PSD cone. Yeah, and similarly, if I have a gram spectrahedron coming from a polynomial, okay, I can look at which happens to be symmetric, i.e., it's fixed under the group action of the symmetric group. Then I can look at all representations of this polynomial, symmetric polynomial, in terms of symmetric matrices that happens to be in the fixed point space. Okay. So that spectrahedron I'm going to call the symmetry adapted gram spectrahedron. Okay. Okay. So the picture you should have in mind is the following. Yeah. So here's the picture. The blue cone here is a cartoon of the PSD cone. Yeah. Of the usual PSD cone. I'm intersecting it with the green subspace, the affine subspace, to get a spectrahedron. That's the green ellipse in the middle. Yeah. All right. So now let's say my the symmetric group is acting, and my polynomial that I started is symmetric. Okay. Then I can cut this PSD cone with the subspace of fixed with the matrices of the consist of the fixed point space. Yeah. That's sort of the yellow subspace, and that gives me another cone. That's the symmetry adapted PSD cone. And furthermore, okay, if I cut the original spectrahedron, okay, gram spectrahedron, with this new subspace, I get in the middle of the red line. That's going to be the symmetry adapted gram spectrahedron. Okay. So I'm basically, by doing this, I'm sort of taking a slice, okay, slice of the gram spectrum I might be interested in, yeah, and try to get some information from the slice from the slice to the original spectrahedron. Okay, I hope I'm making sense. Okay, okay. So here is a typical result. Okay, if you sort of go with this program. So suppose I'm going to go back now to the symmetric sextic case. Yeah. Suppose I have a polynomial in two variables of degree 6 homogeneous, which happens to be SOS. Right? So it turns out that in this case, yeah, there are precisely 4 symmetric matrices, okay, Q of rank 2, 4 guys, okay, such that they are fixed by the action of the symmetric group. Yeah. Okay, there are 4 of them. Moreover, the boundary of the symmetric gram spectrahedron is this spectrum is 2-dimensional, yeah, and it's defined by 2 parabolas. Yeah. Okay. And 2 of those, possibly up to 2 of them, up to actually 4 of them, could be real. Yeah. So let me try to draw a picture here. So here's what I'm saying. Yeah. So you have your original binary sextic gram spectrahedron, and we're cutting it with the subspace of a fixed point, the fixed point subspace. The result is a 2-dimensional spectrahedron, okay, which is defined as the intersection of 2 parabolas. Yeah. And you get up to 4 rank 2 matrices on its boundary. Yeah. So, I mean, you might say this is not very surprising, right? Because here's the sort of the typical picture. Let me go back of a binary sexist gram spectrahedron, right? I'm slicing it with a subspace, and the result is a 2-dimensional thing like this. Yeah. Yeah, I'm not claiming that's sort of an earth-shaking thing, but the point here is that by doing this, I simplify, and I can get some information, yeah, from the earlier one, for the earlier spectrahedron. Okay. All right. So let me now tell you in the last 6-7 minutes, okay, a variation on a very classical result. Yeah. So this theorem is known. I don't think it's attributed to anyone. So if you have a binary form, okay, of degree 2D, which happens to be non-negative, i.e., has sum of squares, then the gram spectrahedron, the original gram spectrahedron, will always contain exactly 2 to the d minus 1 vertices on its boundary that happens to be rank 2. Okay. And there is a very nice way of getting actually these 2 to the d minus 1 vertices from the roots of the polynomial f. Okay. So by looking at the roots of the polynomial f, you can write down these matrices. Okay. So this is a well-known result, and like this is in a sense starting point of Klaus Scheider's paper. In a sense, yeah, he says, what can we say about these rank 2 extreme points? Yeah. Okay. So here is a symmetric version of it. Yeah. Okay. So symmetric version. So if I have a binary form of degree 2D that happens to be sum of squares, but at the same time also symmetric. So I'm looking at the symmetric binary form of degree 2D now. Yeah. And I'm looking at now the symmetry adapted gram spectrahedron, i.e. the slice. Okay. By a very similar but slightly more complicated theorem, okay, we can prove that when D is even, this gram spectrum, this symmetric gram spectrum is going to have 2 to the D over 2 matrices of rank 2. So out of the 2 to the D minus 1 vertices of extreme points of rank 2, this many of them are going to survive in the symmetry adapted gram spectrahedron in the slice. And if D is odd, then 2 to the D minus 1 over 2 of them are going to survive. Yeah. So again, going back to this picture, okay, what I'm saying is that the green ellipse there was the original gram spectrahedron. It had 2 to the D rank 2 extreme points. When you slice it, okay, depending on these even or odd, okay, about half of them, okay, are going to survive. Yeah, in the gram spectrahedron when the symmetric version. Yeah. So maybe slightly again a variation on this kind of result. Let me tell you this too. So if you do have such a binary form, okay, one more time, it's a binary form, homogeneous, right? Degree 2D. I'm assuming it's sum of squares, and let's assume small technical assumption that we have distinct roots for this polynomial. Yeah, and D has to be at least 5. Yeah, so this has to be more than the octets. Yeah. So in that case, okay, if you take a rank 2 extreme point, I call it vertex, but I should call it extreme point, rank 2 extreme point of the original gram spectrahedron before I slice, yeah, okay, which is not in the slice, yeah, it's off of the slice, yeah, it's not symmetric in the sense that it's not in the fixed point space, yeah. Then there is a twin for this guy, yeah, which we call the antipodal rank 2 extreme point Q prime. Yeah. So these two vertices, these two extreme points do not lie on the symmetry adapted gram spectrahedron. It's not one of the vertices that survive. Yeah. But if you take the edge between them, yeah, take the convex hull of the two guys, exactly the midpoint will always be a vertex, okay, of the symmetry gram spectrahedron, and this vertex is going to generically we have rank 4. Yeah. So not only we can say, you know, which ones and how many of the rank 2 extreme points are going to survive when we symmetrize, okay, but we can also create new extreme points, but now of rank 4, okay, from the old guys by this geometric construction. Yeah. So let's see. I guess I want to say something here. Oh, sorry. What was I? Okay, I was going to say something here. Yeah. So I was going to say, oh yeah, here's one. I want to finish with this one. So this back to the binary optic case. Remember, gram spectrahedron had 8 extreme points of rank 4, rank 2, with into 2 classes, and then the edges, okay, between them were edges of the gram spectrahedron. Yeah. So it turns out that only one side, only 4 of them, like Q1, Q4, Q6, Q7, happens to be symmetric in the sense that the action of the symmetric group fixes them. Yeah. So these four of them, Q1, Q4, Q6, Q7, which I call them, okay, happens to be on the symmetry adaptive gram spectrahedron. Okay. The other four are not. Yeah. Which says that these edges, which were on the origin gram spectrum, are not edges on that do not survive on the symmetry adaptive version. Yeah. So I was just sort of removing all of those guys. So this is a sort of maybe a negative result in the sense that we do get some information by doing this for the original gram spectrahedron, but we also lose quite a bit of information too. Yeah. Okay, so I think I'm up with 30 minutes. Thank you for listening.
Thank you, Serkan. So I think we have a few minutes for questions.
Yes. Florian, did you look up? Is it only two?
You're right. There are three.
Yeah. Okay. Exactly. So I knew there's more than two. One of them doesn't work, so only two works.
Which brings me to my question, which is, so what would you expect in general for the combinatorial types if you go higher than degree 6? Like, should I expect them to always be very dense, the polytopes that I get as the convex halves of extreme points?
So yes, we can generally say, and I have to be careful to make the general statement here, but we can say they are high neighborly polytopes. Okay, that's simplicial high neighborly polytopes. That's all I can say. Yeah. And I have to remind myself what exactly high neighborly, but like, you know, it's pretty high. So this was like in this case on the 1 neighborly, but it becomes 2 neighborly, 3 neighborly, 4 neighborly as the degree goes up. Yeah, in that sense, if I guess that's what I mean by dense, I guess. Yeah, they are, the vertices are really connected with each other.
And
but I think
usually symmetric.
They you mean, yeah, I mean there is a net. Oh no. I mean, no, they're not symmetric. They're not like centrally symmetric. No, they're not. These gram spectra. I mean, I drew a very nice one for you, but they could be sort of really oblique, right? So then you don't get symmetric polytopes inside them. No. But I mean, I think though the combinatorial types are a bit hopeless, I think. So, but we can say something about neighborliness. That's for sure. Yeah.
I also have one question. I mean, I'm just trying to think
Yes.
if we extend this problem for non-negative polynomials over a semi-algebraic set, right? So if we look at the sum of squares problem, not over Rn, over a semi-algebraic set, I mean, is this a easy way to extend the results, or there is drawbacks? I mean, I don't.
So, I mean, so, okay, what is it then? So do we have, again, a gram spectrahedron, or what do we have? We have,
yeah, I'm looking at the main result here.
yes.
So I assume that you are only considering sum of squares, right? That's the
Only sum of squares here, overall, overall reals, yeah? So
where, yes.
not sum of squares over another, for a restricted set, yeah?
Right. So then what happens? I mean, is there any easy way to extend it for polynomials over semi-algebraic?
I can see. So let's see. So what have people done? People have done the following thing, right? They said, instead of doing sum of squares over, over Rn, let's do sum of squares over a variety.
Right.
Over a real variety.
Mm-hmm.
So I think that could be done here. I'm not going to claim any results, but I think that case can be used or can be extended to that particular case. I mean, so there is a result, right? The sum of squareness result in that case as well. I mean,
so
you have to,
is there any reason that you can only do it for varieties, not for like semi-algebraic set? I mean,
is there a reason? Yeah, I think in the variety case, so this this condition that your polynomial is sum of square if and only if the matrix in the middle is positive definite, translates in the case if I have to do all of this modulo an ideal. Yeah, it's
right. And perhaps you probably need a Grosvenor basis for
exactly. But I'm not sure that something such simple can be done if I do it over a semi-algebraic set. I don't think so. Although maybe like if we invoke things like positive Stellensatz, you know, maybe it can be done. It might be possible to do that in that case. Yeah, but I don't know the quick answer for it.
All right. Thank you. Any other question for Serkan? All right. If not, let's thank Serkan again, and thank you all for coming to this seminar. And I hope you enjoyed the rest of the day. Have a good day.
Thank you. See you.
Thank you for coming. Appreciate. Thanks for the questions too.
Thank you for accepting our invitation. Have a good day. Thank you.
Take care.